In this video, we're going to look at how randomization can be used to make a hypothesis test have a specific significance level. So let's say we have one random observation. So we have one value of data. We have a random variable x which follows a binomial distribution with 10 independent trials, and the probability of success on each independent trial is theta, and that is the unknown in this situation. We wish to test the null hypothesis that theta is equal to 1/2 against the alternative hypothesis that theta is equal to 1/8. So in order to support the alternative hypothesis, it would make sense that we would do that when x is on the smaller end of the spectrum, right? Because if we observe if we have only a few successes out of the 10 independent trials, then that would support the notion that the probability of success on any one trial is a little smaller. Whereas if we have, say, 4 successes, let's say x equals 4 or x equals 5 or something like that, then that supports the notion that success on each trial is 50-50. So you can see here that we're going to choose the rejection region that we see here. So let's suppose that we will reject the null hypothesis in favor of the alternative if we observe x equals 0, x equal 1, x equal 2. And recall that here the decision that we have to make is whether to reject the null hypothesis or fail to reject the null hypothesis. So the action space here we'll call A0 the instance where we fail to reject, and A1 is where we reject the null hypothesis. And I just noticed I lost my 1. Okay, so let's find out what level test we have here. Remember that the level of the test, the significance level, is the probability of a type 1 error. So that's the probability that we reject the null hypothesis given that the null actually is true. So that's the probability associated with this occurrence here, given that H0 is true. So the probability that x is an element of 0, 1, 2, given that theta is 1/2. And if you have a TI calculator, you can use the built-in functionality there to compute these probabilities. Otherwise, you either have to do it by hand or you may have access to some other technology that will do that. But I do recommend, if you can get your hands on a TI calculator, it's super easy to compute that probability. And so really what we're looking for is the CDF for this distribution evaluated at 2, right? Because that CDF is the probability that x is less than or equal to 2, and in this case, given that theta is 1/2, which is exactly what we need to know. And so in the TI calculator, the command is binom CDF. You can access it by clicking the second button and then clicking the vars button. And then above the vars button is DISTR, which stands for distributions. And then you just tab down to where you find binom CDF and you enter what you see here. Okay, so what we get is 0.0546 and some change. That is the significance level of this test. Now, common significance levels are like 0.01, 0.05, 0.1. So in part B, what we want to do is look at how can we modify this test in order to guarantee that our alpha is something like 0.05. Because since we're dealing with a discrete observation here, there's only a finite number of significance levels possible if we just stick with the standard way of conducting these hypothesis tests. But with randomization, as we're going to see, we can get any significance level we wish. So that's what we want to do. We want to see how can we modify this test using randomization to get a significance level exactly equal to 0.05. And the key is in the maximum value in our rejection region. So let's, just for reference, let's zoom in a second. And remember that our rejection region for part A was the set consisting of 0, 1, and 2. And that led us to this test with a significance level that's close to 0.05. And then if we evaluated the cumulative distribution function at x equal 1, then you see we would have a value of 0.0107 and some change. And then at 3, we get something bigger than 0.1. So if we observed either zero successes or 1 success from our data, then it would be clear we should reject. If we observed 3 successes or more, it would be clear that we should not reject. The question is, what do we do if the number of successes we observe is 2? Then how are we going to deal with that? So let's see, what do we do there? And like I said, the key is in that maximum value, that 2. Because as I mentioned earlier, if we observe x equal to 0 or 1, then we reject the null in favor of the alternative. Because that would definitely be few enough successes that we have strong evidence to support the alternative that the probability of success on any one trial is less than a half. There's more support for the alternative here that theta is 1/8. If, however, we observe x bigger than or equal to 3, we would not be able to reject the null hypothesis. And so notice that in these two easy situations, as soon as we observe the data, we do actually have a probability distribution on the action space. It's just that we do one action or the other with probability 1. And then, like I said before, the interesting case is, what do we do if x equals 2? So we want to make this test have a significance level exactly equal to 0.05. And so the key here is that we will reject the null hypothesis with probability little p and fail to reject with probability 1 minus little p. And so the question is, what little p works? So the idea is that when we observe exactly 2 successes, then we quote-unquote flip a coin of sorts. But it's not a fair coin. It's going to be an unfair coin. But it's going to be unfair in such a way that our significance level for this test will be exactly what we want. So let's simulate a random variable y, which is uniform from 0 to 1. And it's important to note that this random variable y needs to be independent of the random variable x and have nothing to do with theta. So what we're going to do is we're going to reject h0 if our random variable y is in this interval from 0 to little p, and then we'll fail to reject if it's in this interval from little p to comma 1. And so now let's see what little p will work to make our significance level exactly what we need it to be. All right, so we're looking at the probability that we reject H naught given that the null is true. And so that's going to be equal to the probability that x is less than or equal to 1, given that theta is 1/2, plus the probability that x is 2 and that random variable y is in this interval from 0 to p, given that theta is 1/2. Since x and y are independent here, we can do the probability of that x is equal to 2 given that theta is equal to 1/2 times the probability that y is an element of 0 to p given that theta is equal to 1/2. But for that second part, y and theta have nothing to do with each other, right? They're independent. So we can get rid of the condition there for the second part. And so then calculate these probabilities, and then we just have an equation that we need to solve. And we see that if we use little p equal to 0.8933 roughly, then we will have the desired significance level that we want. So here is the randomized decision rule that we have put together. So given the data we observe, right, remember a randomized decision rule, once we observe data, is a probability distribution on the action space. And so remember we said if we observe x less than or equal to 1, then we know that we're going to reject with probability 1. On the other hand, if we observe something 3 or bigger, then we're going to reject H naught with probability 0, which means we are not going to reject. Whereas the interesting case is when x is 2, and in that case we will reject H naught with probability p, and then fail to reject with probability 1 minus p. So remember, this is the case where we have to, quote unquote, flip the coin, so to speak. But it's not a fair coin. It's a coin which will tell us to reject H naught roughly 89% of the time, and fail to reject H naught the rest of the time.